I'm going to talk about representation learning, more specifically self-supervised learning, which is my area of research. I'm a PhD candidate here at the University of Campinas, advised by Professor Zelio and Adine Ramirez, that you might know. Yes, let's start off. So throughout the presentation, we're gonna go throughout the path of self-supervised learning since it kind of started, at least this new era of approaches. We're going to talk about some of the limitations that current methods have, and I will use those limitations to motivate some of the work we have done throughout the years, and present those works as an attempt to solve such limitations. So the modern pipeline of machine learning is very clear, and it's been implemented for quite a while already. So for a number of years, let's say 3, 4, even more, we have this two-stage pipeline, let's say, where basically most of the very large systems today follow, which is basically composed of a round of unsupervised or self-supervised pre-training. So this is the round of training that is mostly costly, and also takes the more time and more compute, more resources, more everything, basically more data. And then after this very expensive and time-consuming round, we have more specific kinds of training using the foundation model, let's say, to basically learn and apply the general knowledge to basically guide to new specific tasks, to tasks that we mostly care about. So that's basically the two-stage pipeline the modern machine learning follows. All the big systems from GPTs and all kinds of language models mostly follow this very same two-stage protocol. And for vision, it's not different. But to start off, we basically need to know two concepts basically. One is the concept of representation learning, which is basically this idea of extracting meaningful patterns from data. And representation learning is this very big umbrella. It basically encompasses all of machine learning, if you care. So basically, representation learning can be done using supervised learning, can be done using unsupervised learning, can be done using RL. It doesn't. It's very general. But more specifically to this talk, we're going to talk about self-supervised learning, which is basically an approach, a way of doing unsupervised learning. And the way self-supervised learning mostly differs from current and more classic unsupervised learning methods such as k-means or BCA is mostly the way, or basically the source of labels come from, the way we mine labels basically. So instead of, as we're going to see, instead of using labels from humans as supervised learning does, self-supervised learning finds ways of extracting labels from the data, and that's basically the biggest difference that tells it apart among the other unsupervised learning groups of methods. And this new resurgence, let's say, of course, if we go back in history, we're going to see very similar work already done that could be classified as self-supervised learning, way before the 2000s, for example. But this new resurgence, I would say, started with those puzzle tasks, let's say. And here I have like 4 classic examples of self-supervised learning methods that were published like in around 2016, 17, 18. And it's basically this idea of creating a task that, in order to be solved, makes the neural network will need to learn some kind of semantic understanding of the data. So take the one in the bottom right corner, for example. That's predicting rotation angles. That's very simple. So you basically define a set of rotation angles, let's say 0°, 90, 180, and 270. Then you pick an image and then randomly choose one of the rotation angles and apply to the image. So then you just pass the rotated image to the neural network, and all of a sudden you have a four-way classification problem now, because what you're going to do is basically challenge the network to classify, to predict which rotation angle did you apply to the image. And since you have established four rotation angles beforehand, so you have this four-way classification problem, where the neural network basically needs to find out or predict the rotation angle applied to the image. And if you think about it, in order for the neural network to excel in such a task, it needs to learn, it needs to pick up some important patterns of the world. So imagine, for example, an image of a tree, like and you basically rotate this image by, let's say, 180 degrees. So now the leaves that are at the top, at the bottom of the image, right? And the sky is also might be on the bottom of the image. The root of the tree is now at the top. So for the neural network to basically know, okay, this image was rotated by 180 degrees, it needs to know that, okay, this image looks weird, basically. Usually when I see images, the sky is at the top, right? The ground is usually at the bottom. The leaves are usually at the top of the root of the tree, not at the bottom. So it needs to pick up those semantic characteristics of images, and basically information of how the world works, basically. So another one, if you care about this, the one in the bottom left corner, for example. So you pick it very simple as well. You pick an image, you then mark like what are gonna be like some kind of an anchor patch, like the patch in the middle, for example, and then you sample patches around it, right? In this case, you have 8 patches around it. So then you can ask, okay, what's the relative position of the patch in the middle with respect to, let's say, any one of the patches around it? Let's say the patch number 3, for example. What's the relative position of the middle patch with the patch number 3? So now here again, you have a classification problem, but now it's an 8-way classification problem because you have 8 possible outcomes here, and it's basically the same thing as before. So now again, to solve this test, the neural network needs to learn some special characteristics of images. For example, in this case, for example, you have like the face of the cat is in the middle, is in the anchor patch, and patch number 3 is the ear. So the neural network needs to somewhat know that the ear should be on top of the eyes, a little bit to the right, and stuff like that. And it's the same for the other ones. So this I will call this the classic methods, even though they are not that old. So that's the idea, to create and optimize those puzzle tasks that doesn't require annotations from humans. Instead, annotations come from the data themselves. And but I should say those methods have evolved and matured. And now, as we're going to see, current methods are basically based are based on 3 important pillars. What I like to call them 3 important pillars of current self-supervised learning methods, and they are: the first one is this idea of synthetic view generation. It's very simple, just an idea of creating different views or different viewpoints of your input. It's very similar to, for example, looking at an object for a different angle or from a different perspective, from a different distance, something like that. The idea of a joint embedding architectures very prevalent today, which is basically this idea of having 2 separate encoders. So these encoders might share parameters, they might be different, they might receive different modalities. It doesn't really matter. The thing is that they will receive one of those different viewpoints or perspectives of the image and output a representation vector. which is represented by the H there. And lastly, those representation vectors are optimized using some kind of similarity-based loss functions. Similarity-based loss functions. So that's basically the three pillars of current self-supervised learning methods. And those are more recent ones, recent methods, recent self-supervised learning methods. So we have, and here I try to put like methods that work in different ways. So for example, the one at the bottom, at the top left corner is contrastive learning. So for this one, you need to have like some kind of two positives and at least one negative. And the idea is, okay, the positives should be close together in the embedded space and at the same time far away from the negatives. But we have like a large number of methods. Like the family of self-supervised learning is very rich now. So you get like the reconstruction-based methods, MAE, for example, very similar to an autoencoder, which basically learns representations by reconstructing missing regions of the input. You have like the clustering-based methods, which so instead of working directly on the embedded space and the representations, it basically tries to discretize the embedded space by learning those prototypes or centroids. Yes, there are like the family is very large now. But despite the recent advances, and the advances are real, if you take like the over the years, throughout the years we have observed some important limitations of current methods. To begin, most of the SSL methods before have like exhibit like a performance decrease when their representations are used to learn downstream data prediction tasks. And here, what I'm talking about is, okay, you pre-train the embedding the encoder first, right? You do the self-supervised, unsupervised training round first, and then once that's done, you're gonna use your learn representation to learn a variety of downstream tasks. And if those downstream tasks are tasks that require dense predictions, such as object detection, segmentation, and so on, you usually will see some kind of performance decrease. Most of those methods are very prone to collapse, and we're gonna talk more about that as well. And basically, those methods are very difficult to train by nature, and basically because we don't have labels, right? Since we don't have labels, the self-supervised signal is very noisy, and to train those methods, we usually need to come up with some clever way to avoid like trivial solutions. And lastly, most of those methods, they always use interview statistics, like statistics or information that comes from the views themselves. And since the views come from the same image, you never get to explore relationships between different images. So those are the main limitations that we have observed over the years, and we'll use them to basically motivate some of the methods we're going to present now. So to begin, let's start with the first one. So the first one is this claim that most of SSL methods, they exhibit a performance decrease when their pre-trained representations are used to learn downstream data prediction tasks. So we set out to basically try to come up with an approach that better trades off classification at a course level with tasks that require dense prediction. So based on this motivation, we proposed this idea of a contextualized local embedding method. So this is, we call this method CLOVE. It's basically self-supervised learning of contextualized local embeddings. We presented this on ICCV on a workshop back in 2023. And the motivation here, let's start, is basically this. So we have observed that most methods, and that's actually most of them really by the time we were doing this work, they usually learn like a global representation for an image, right? So you have a view or an image, whatever, and you're gonna try to learn it like a single vector for it. The single vector should basically contain all the relevant information for the image. But it was also we started to show up some methods that instead of focusing on like a single representation for the entire image, uh, those new methods were more local level representation methods. So they basically try to come up with optimization tasks that were done at like specific regions of the image, such as small patches, for example. And then we come up with this idea of a contextualized representation, which is not a global representation and nor it is a local level representation. Instead, the idea here is that okay, we're gonna we want to learn a contextualized vector that will encode all the information of a larger part of the image. But this part of the image needs to be correlated. So you can imagine, for example, in this image I'm showing you, the 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 patches that incompatible that the patches of the sky, for example, of the image. All of those patches are very similar, so it doesn't make sense to learn a representation, a separate representation for each patch of the sky, for example. So instead, we want a contextualized representation that takes all of the sky, for example, in consideration. And the same could be said to the ground, for example. The ground there is very similar across many patches. So the contextualized embeddings should basically pick up all the regions or the larger regions in the image that are semantically similar. So that's basically the large architecture of the method. In here, we're gonna see like the three pillars of self-supervised learning we talked about before. So as you can see, the first one is synthetic video generation. So from one image, we create two others, right? Following like geometric and pixel intensity transformations. But here, when we create those different views of the same image, we're going to come up with a system that we know that where one pixel in one view is located on the other view, if they are there, of course, right? When we create views of an image, we usually take different crops of the source image as depicted there. And these crops usually have like an intersection region. So we basically want to know, like for example, the pixel close to the eye of the dog in the view one, where it is on view two. So we want this mapping basically. And that's clearly because here we used convolutional neural networks by the time. But instead of doing like a global average pooling as CNNs usually do, we removed the global pooling, basically to avoid signal decimation, because that's what global pooling does, and worked directly on the final feature maps of the convolutional neural network. So now it's very similar to a transformer at this point, because instead of having like one single global vector, you have log all the feature maps of the image. And by knowing the maps that I talked about before, like one pixel in one view is at the other view, we can now learn this contextualized module here, which is basically a normalized self-attention method that will take into consideration the similar regions in the image, the regions in the image that share semantic characteristics, and create the contextualized feature maps now. So as you can see, a single contextualized feature map now is a combination of many local features from the images, from the original image, and of course local features that correlate between themselves. So think about the image of the sky again, right? Or in this example, the background, which is mostly blue. So a contextualized feature vector should basically take into consideration all the background there, because the background is very similar all across, while different contextualized embedding should take care of the dog, since the dog is also very similar in color and texture. So lastly, we apply this margin loss function, where we basically go over the matching features using the mapping that I talked about before, right? Where we know like where pixels went from one view to the other, and use the contextualized vectors to predict the local vectors of the second view. So the contextualized vectors of view number one are used to predict the local vectors of feature number two. And since we know, like we know the exact mapping because of the mapping, so optimization is done like in a good way here, in the right way. And at the same time, to avoid collapse, and basically to make sure that the contextualized vectors are different from each other. Like those contextualized vectors will learn different feature components. We also apply this negative term here, which basically enforces a contextualized vector to be unique. So, okay, this was pre-training, right? After it pre-trains using this architecture on a large corpus of non-annotated images, and then we can now see how those the pre-trained features perform. And here I'm showing you at the left object detection, and at the right dense pose estimation, two dense prediction tasks that require like the features to have like finer information, fine characteristics from the images. And at the time we managed to perform well against competitors that basically try to perform the same. And those are qualitative evaluations. So now you take the same pre-trained features and try to come up with and try to learn key points or dense pose estimations, for example. So key points at top row and dense pose in the bottom row. Okay, so going to the second now motivation. So many of this, we claim that many of the self-supervised learning methods suffer from mode collapse. And mode collapse is basically one of the biggest challenges when training self-supervised learning methods. So we basically set up to okay, can we create a method that is like less sensitive to hyperparameters, for instance, that is less sensitive to collapse, and that also avoids a lot of normalization techniques that are used to avoid mode collapse, and that's the objective here. So then we proposed this method we call CARP. We presented in 2023 in Europe at New Orleans. And the idea here is, so before going into the method, we need basically to compare these two kinds of self-supervised learning methods. We have these two general kinds of methods. We have the embedding prediction methods and the clustering methods. As I said before, embedding prediction methods work directly at the embedding space. You pass the images through the encoders, you get the embedding vectors, and then you apply a loss function directly on the embedding vectors. Clustering methods, they discretize the embedding space, they learn prototypes. Both methods, however, can go wrong very easily. In embedding prediction, the neural network might just find a shortcut and optimize the loss function by just learning a constant embedding. And in clustering, it might just optimize the loss function at the same way by putting everybody at the same centroid, for example, and the same prototype. And of course, we don't want those trivial solutions because those trivial solutions doesn't learn any kind of useful representations that we can use. So of course, throughout literature, we're going to see a lot of techniques to avoid such trivialities. And we set up to basically propose another one here, another one that avoids some of the limitations of the existing methods. So here again, let's go over how the architecture works. So we have like the views, right? the synthetic view generation again. So the views are passed to the joint embedding architecture. So now we have this projector, which basically reduces the dimensionality of the input image and gives us a vector. So now the vector goes through an assigner, which is basically like a linear layer that learns prototypes or centroids. And then you're going to have the probability distributions relating the views to the centroids. So most methods stop here. They basically will apply a loss function to make to enforce that the distributions here will need to be similar across views of the same image, but of course they cannot collapse, right? They cannot the neural network cannot put everybody at the same prototype. So for that they use like techniques such as the sinkhorn knob or centering, a bunch of techniques to avoid that. So here our idea was a little bit different. So imagine you are in the space of features, right? So the views are projected in the joint embedding architecture and give embedding vectors, and these embedding vectors sit somewhere in the prototype space, in the embedding space, right? So then we have the prototypes. We have the prototypes. The prototypes will, of course, start randomly at the beginning of pre-training. But instead of using all the prototypes at once, like all the methods do, and pose the optimization tests across all the prototypes, or basically divide the prototypes into subgroups. So the subgroups will be picked randomly. And in this example, you might like choose the green ones, the green squares, and the red circles. So now we're gonna make an optimization task over the subgroups. So basically we're gonna assign the views representations to a specific subgroup, the subgroup of the blue squares, and we're gonna have something like this, like distributions that we're gonna optimize for consistency, and do the same for the second subgroup. And one important thing here is that those subgroups, they are created randomly, and they need to be they are recreated at each iteration. So at each iteration, at each batch, basically, different subgroups are created. So the neural network can never rely on a specific subgroup. The neural network never knows to which prototypes the views will be compared against. But the only constraint here is that the views should be consistent across subgroups. However subgroups are, however they it doesn't matter. But here, one important aspect is this idea of randomization. And this randomization property when creating the subgroups of prototypes basically introduces a regularization effect that basically prevents collapse altogether. And to have an idea, we can train this without any kind of extra regularizers, such as sinkhorn knob or centering or whatever. It just need to recreate the subgroups at each iteration, and you're going to be fine. So the method is much more robust. It's not like susceptible to hyperparameters of the sinkhorn knob, for example, or any other hyperparameter. And this is actually one of the great achievements we had. So here I'm showing you, okay, after pre-training again, right? We pre-trained the system using this idea of random partitioning. By the way, this is the name we call this idea of creating those random subgroups of prototypes. We're basically partitioning the prototype space into subgroups. So after pre-training, we can now use the representations to learn a bunch of other tasks, right? And here I'm showing you KNN performances, top 1 accuracy on eight different data sets. So you basically learn 8 different tasks. And as you can see on average, and actually in most of the individual data sets, our method, CARP, performs really well. So here I'm showing you now MAP, mean average precision on Pascal VOC, and top 1 accuracy on iNaturalist. And here is a different benchmark. Here, for example, you can see those n's here, n equals 1, 2, 4, 8. This is basically the number of annotated examples per class that we gave to the model. So basically in the first column here, the neural network should learn Pascal VOC with only one labeled example per class. And the same goes on with the INET. So going to the third motivation, third limitation, we also observed that most of SSL methods only use interview statistics. So again, the idea of creating views, for example, when you create views, you take an image, you augment it multiple times, right? 2 times, for example, and you have 2 versions of that source image. And then what most methods do is, okay, let's optimize those two views to have similar representation vectors because we know they come from the same image. So that's basically the source of supervision there. But as you can see again, the statistics, the information comes from the source, a single image. Even though the 2 views might look different because of the geometric transformations you applied, the statistics come from a single image whatsoever. So in order to try to come up with to solve this issue, we come up with this new memory-based non-parametric approach. And here we actually took some inspiration on the role of memory on biological systems. And we presented this work on ICML last year. We call it NACEL, and it's basically, it stands for non-parametric memory augmented self-supervised learning of visual features, like a mouthful. But the key idea here, and I thought about that a lot when I was writing this paper, was this idea of how important memory is on living systems like us, for example. So for example, when a child sees a new concept for the first time, let's picture that. So a child sees a dog, for example, for the first time. We will clearly see that this child will get very excited, right? It's a dog. It barks. I don't know. It's cute. So the child will get very excited. But I don't know, the next day or next couple of days, let's suppose this child sees re-encounters like the same or like a different dog, like the same dog or a different dog, whatever. You will see that this child will not have like the same level of excitement as before, as excitement as the first time. And that's basically because he or she already saw a dog before. So it might get excited, might recognize a dog, for example. And for sure it will recognize because when it sees a dog, one of the things that we're mostly certain is that it basically refers back to memory, to the memory from before almost immediately, right? The second the child sees the new dog or a different dog, it will basically refer back to memory. And that's the idea of the idea of using memory to correlate or to contrast, to correlate what's being seen at the moment with what has been seen in the past. So this is the general idea, again, the general architecture. It's very similar, so you must be familiar already with this kind of architecture. We again have the view generation process, the joint embedding architectures that produces embedding Z1, Z2 here. But now we have this component in the middle here, which is the memory. And this memory basically will store representations from images that we saw in the past, right, on previous iterations, for example. And this big memory basically behaves like a FIFO structure. So you can imagine new feature vectors coming from one end of the memory and going out from the other end of the memory. And but now we have this idea of a memory block. And a memory block is basically a sample from the original memory, a random sample from the original memory. And that's basically the motivation here is basically to break a correlation in the large memory because, well, because the large memory here works as a FIFO structure, data structure, you can see that you get this time related correlation because in one end of the queue you're gonna have very fresh like new representation factors, while in the other end of the queue you're gonna have like old ones basically, and in the middle you have this range, right? So in order to break this time axis, we sample a random like random features, random memory representations from the memory component and create these memory blocks. So now what basically is left is to compare what's seen at the moment, in this case, the representations of the orange dog with the representations that we saw before that are now in the memory blocks. And now we're going to have those probability distributions. And in this example here, just to be intuitively clear, we want the 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 level of similarity of the orange dog, which is what we see at the moment, to be very high with this other dog right here, the M8 memory representation. And that's because that's a dog as well. Of course, we don't know the labels, right? We don't know that's actually a dog, but since they share uh, features and more specific class level features, we want when we compare the representation of the current dog with the representations in the memory, we want the representations of the orange dog to activate this region of the memory, the M8 region, because because it's a dog and the other ones are like not related. So that's the intuition here. So we want uh, the thing we're seeing at the moment to activate regions in the memory that correlate to the input signal. And then what's left is basically just optimize the views for consistency. So basically the two views, since we know the two views come from the same image, they should activate similar regions in memory. They should activate similar representations in memory. So when compared to the random block of memory, they should produce similar representations. And again here, since this idea of a random memory block, it's very similar to the idea of random partitioning back there. It's kind of inspired actually, because the memory blocks are created randomly. And again, this idea of randomization here, it helps a lot because it introduces again a regularization effect that basically prevents the neural network from collapsing, prevents the self-supervised pre-training from collapsing. And we don't need any extra regularizer, as a matter of fact here. You just optimize this cross entropy there and you're good to go. So after pre-training, you can, of course, take the representations from the pre-training encoder and learn new pretext, new downstream tasks of interest. And here, for example, I'm showing you again 8 data sets, 8 different tasks that we learned using the frozen features from the encoder. Again, here on average, we perform really well against the competition. And here is a very very interesting task. Is basically image retrieval task. So I give you an image and there is a data set. So I give you an image and your task is basically to go to this data set and fetch the most similar, most closely semantic images from the data set. And again here, our VITs perform really well. And by the way, in this we use VITs, and here where we can see, for example, some interesting visualizations regarding what the self-attention layers of the VIT learned. So again, this is completely unsupervised pre-training, only using this idea of a memory and correlating what's seen at the moment what has been seen in the past. The neural network can learn attention layers that basically segment objects. And you can see that the segmentation is quite complex in some examples. In the second image is the image of this monkey here, for example. You can see that the patterns of self-attention can clearly segment like the body part of the monkey, like as well as the front face and sort of the hair there. And the same thing happens with the other images. For example, the bird here, you can see like the beak of the bird, uh, very well delineated, very well segmented. So here another qualitative example. You can take different images, like in the second row, or views of the same image in the first row, and basically do some kind of patch correspondence task. So basically, for each image, you compare, you take the patch, you patchify the two images, just like a transformer does, and you basically compare, like, from one image, what's the most similar patch in the other image, right? And by doing that, you can basically learn those kind of correspondences. At least see if the features get those, have those correspondence features in there. So in the top row, it's somewhat easier task because they are images of the same views of the same image. But in the bottom row, you have actually different images of the same class. So those are different images, and even though they are different images, the correspondence can be done quite well. I believe that's it for me. Hope I made the time. Thank you very much for listening, and of course, I'm open for questions.